is that we're going to have a litany of tests that we're going to be able to use as tools, right? We learned about t-tests, we learned about confidence intervals, we learned about analysis of variance last week. This week we're learning about chi-square. Next week we're going to be learning, and the week after we're going to be learning about correlation and regression. So we have a whole series of tests that we have available in our toolbox, right? Just like if you have a nail, you're going to get a hammer out, right? But if you have a screw, you're going to get a screwdriver out. We're going to want to make sure that we use the appropriate test to the situation that we have, to the analysis that we need to do, and the kind of data that we're working with. Okay, so up till now, when we were talking about t-tests, right, we were talking about numerical data, right? We're comparing the mean of one group to the mean of another group, and to get a mean, you have to have numerical data. You have to have a scale or set of numbers. Analysis of variance was an extension of that. Instead of having two groups, now we could analyze the means of group A, group B, group C, group D. You can have multiple groups, analyze them together. So now we're missing a way to handle categorical data, right? So that's what we're going to get into tonight. Chi-square, odds ratio, relative risk. Those are ways for us to deal with categorical data. For instance, I'm going to start off with something like a really simple example here and say to myself, okay, let's say I have a sample of 200 people from a population. Okay, now some of those people are going to be left-handed, some of them are going to be right-handed. Some of those people are going to be males, some of them are going to be females. So how many variables did I just mention? Two, right? Gender and handedness, right? So we have two variables, gender and handedness, right? Okay, and how many values do we have for each of those two variables, right? Assuming everybody's only got two hands, right? What's that? Ambidextrous. Well, yeah, okay. I'll tell you what. Hang on to that. For right now, we're going to just record right-handed or left-handed. Okay, we're going to force people to give us an answer of right or left-handed. So we have two values for gender, male and female. Right? We could extend that nowadays too, right? But for handedness, we have left-handed and right-handed. Okay, so now I have 200 people. Well, let's say I give you a little bit more information, and as it turns out, 100 of those people are male, and 100 of those people are female. Okay, now this is just coincidence, right? It isn't. It just happens that 50% of the population, or 50% of my sample, is male and female. I didn't purposely pick out 100 males and 100 females. I'm going to compare them, right? Just the way it happened to drop out. Okay, so now, in matter of fact, maybe just to make it, now I want the numbers to come out easy. So just keep in mind that just happened to fall that way. And let's say that it turns out that of 200 people, 60 of them are left-handed and 140 are right-handed. Okay, a little bit more information that we have about this population. But now let's say if we really go back in and we look at each individual in this population. Subject 1, male, left-handed. Subject 2, female, right-handed. And we decided we wanted to organize that data. One of the ways, since it's categorical data, what we can do, yes?
Got some stuff on the screen there.
Oh my goodness. Okay, so these guys here are not seeing any of this. I'm drawing, oh, there you are. Are you people sheep? Do you think? Tell me that that's going on behind me. I'm not. Am I that intimidating that they're afraid to tell me that?
You're terrifying.
Yeah, I know. Yeah, exactly. Okay, so at any rate, now a nice, convenient way of organizing this data would be into tables, right? Because we only have two possibilities for gender and two possibilities for handedness. So I'm going to make a 2x2 table. Now, just like, remember we were discussing diagnostic tests, it's always convenient to put the exposure in the rows. A lot of times we're dealing with situations where, oh, well, we want to know whether an exposure will cause some sort of negative or positive outcome, whether a drug or a placebo is working better than, will relieve pain or something like that. So just like with the diagnostic test, I'm going to put the exposure, or the test, to be test result kind of, put the exposure into the rows. And in this case, my exposure is gender. I want to know whether or not, gender has some effect, has some association with handedness. And in the columns, I'm going to put whether a person is left-handed or right-handed. I'm going to put left-handed here and right-handed here, but it's not going to really matter that much. Okay, so let's say now we actually analyze the data and we find, well, we know that there is, now this is, let's say, males and females. We find that, well, we know that there's 100 males and 100 females, right? So I can just go straight across. And we know that there's 60 left-handers and there's 140 right-handers, right? So just what we know about this population already lets me fill in those blanks around the perimeter of these boxes. But we don't know what the distribution is in here. So now I'm going to ask you, if there's no association between gender and handedness, what would we expect to be in these boxes? Yeah, what?
30, 70.
Yeah, 30%, right? Each one of them, the incidence of prevalence of left hand, I guess it's prevalence for handedness because it doesn't change probably, right? But we'd expect 30% to be left-handed in both situations. So we have 100 males. How many of them would we expect to be left-handed? 30, right? And so that would leave 70 that we'd expect to be right-handed. And remember we said that whole thing about degrees of freedom. Once I put that 30 in there, this one has to be 70. Once I put that, and then this one has to be, since it adds up to 60, it's got to be 30, and this has to add up to 70. I would expect that outcome, right? That's what I would expect if there's no association. Okay, so now let me see if I had made this 100 and 120 and 80. 80 females, 120 males in our sample, right? What would we expect it to be in those boxes? 30% of 120 is 40, right? And this would be, the difference here would be 80. And 30% of 80 would be 24. And the difference here would be 56. Right? But it would add up to 60 males, 60 left-handers, 140 right-handers, right? We get that same outcome. So basically, this is what I would expect to happen, okay? These are what I would call my expected values, okay? So let's say I really did this study, and it was really, prevalence was 30% of left-handers in this population, and so on and so forth. Would I expect to get exact, if I just randomly picked, 120 people, would I expect to get this exact outcome? Be pretty rare. It's like flipping, if I asked you to flip a coin 100 times, it wouldn't be very likely that you get exactly 50 heads, right? It'd be the most likely outcome, but it wouldn't be even maybe 30% at a time, right? Probably even less than that. Right? We could actually calculate that, right? If we went back to our binomial distribution, we could figure out what the likelihood is of that exact outcome would be. 49 would be pretty likely, 51 would be pretty likely, 48 would be pretty likely. And so same thing here. We would expect to get close to this outcome, right? But not this exact outcome, right? So it's actually likely that we would get an outcome that's slightly different than this, is more likely than getting this exact outcome, in fact. Just like getting, a number of other outcomes other than 50 for heads would be more likely. Okay, so I know that I don't want to see this exact outcome. I don't expect that. But on the other hand, I don't expect it to be dramatically different, to be very different. So those are my expected values. If I were now to go into this population, take this sample, and actually see what I got, those would be my observed values. Right? Those are my observed values. And I would expect them to be a little different, but I wouldn't expect them to be very different. The more different that they are, the more likely it is that there is an association between gender and handedness. Does that make sense to you? In other words, If I see that a lot more males are left-handed than 30%, and a lot fewer females are left-handed than 30%, the bigger the difference between my expected values and my observed values, the more likely for me to justify saying that there is a difference between whether males or females are more likely to be left-handed. Okay, so let's go on and move. Let's take another example. And I have one if you want to follow along. Let me just see if I can't open it quickly. Not there on Blackboard. Let's see. I want this one first, I think. Okay. Okay, here's a group where I have 200 people again. Right. As it turns out that within this group of 200 people, 50 of them use IV drugs and 150 of them don't use IV. This is probably a very high at-risk population, and 150 of this group do not use IV drugs. And as it happens, 15 out of the 50 people that used IV drugs turn out to be HIV positive, and 25 of the people that don't use IV drugs turn out to be HIV positive. Okay, 125 aren't. Okay, so these start out as my observed values. Now, what would I have expected if there's no association in this population between IV drug use and whether or not somebody's HIV positive? Okay, well, the risk of infection, I'm going to go past that for a second. Whoop, I want to come back to that. I guess, I must have got, there must be another one. Did I not start at the top? I'm going to actually just start with that and work on a piece of paper. Let's see if I can't fix it so I can see both of these at the same time. Yeah, that should do it. Okay, so I'm going to duplicate this over here. $15, $35, $50, $25, $125, $150, $200, $40, $160. Okay, this is HIV positive and negative, and this is IV drug user and not an IV drug user. Okay, so let me bring this back over here. These are my observed values from this population. Okay, now I'm going to make another chart here, my expected values. Okay, now there's 50 IV drug users in this study, there's 150 non-IV drug users, so that's fixed. And we know that it's 40 people that are HIV positive, and there's 160 that are HIV negative, so that's not going to change on our expected values. Now, what's the rate of HIV in this population? 40 over 200, it's 20%, right? 0.2. Okay, so if there was no association between whether a person was an IV drug user or not an IV drug user, how many of those 50 people would we expect to be HIV positive? Right, 20% of them, right? Just like the whole population, right? So we'd expect 10 to be HIV positive. We'd expect 40 of them to be negative. What percentage of the 150 that were not drug users? Same deal, right? 30 and 120. So this is what we actually found, and this is what we would have expected if there's no association between whether a person is an IV drug user and whether or not they're HIV positive.
Can you assume the expected values based on what you observe in all cases?
I'm not sure I know what you mean. Like, in other words, our expected values may not be like what the prevalence really is in the population.
Yeah.
Right, because we could get a skewed sample, right? We could get a sample that's off a little bit, right? But what we're really concerned here right now is whether or not our results are so different from what we would have expected that we can say that there seems to be a reason that it seems to be unlikely that we would get that big a difference between our observed values and our expected values.
Chi-square value, just you describe it.
Right. Yeah. So we're going to give that a try right now. So how are we going to describe how different these things are? Well, we're going to look at each cell here. This cell for starters, right? And I'm going to look at the difference between these two cells. The difference between these two cells is 15 minus 10 is equal to 5, right? Difference between these two cells, 35 and 40, is going to be 35 minus 40 is going to be minus 5, right? Difference between these two cells is going to be positive 5. Difference between these two cells is going to be negative 5, right? We can't add them together. We had the same problem that we had with the sum of squares, right? Can't add them together. They add up to 0. So we need to find a way to make it just so that we just are working with the size of these differences, not their sign. So one way would be to work with absolute values. The other way would be just simply to square these differences, right? So 5 squared, negative 5 squared, plus 5 squared, negative 5 squared. So that's going to be 25, 25, 25, 25. So it's going to add up to 100, right? How did we get that? We took the observed values minus the expected values, and we squared them for each one of the cells. Okay? So now we're working with a number that is very large relative to the differences, right? So what did we do when we had that problem when we're working with numerical variables and we're working with sum of squares? We divided by, right? We took the square root to bring it to take the variance and bring it into, took the sum of squares divided by the degrees of freedom, and then we took the square root to bring it back down into the range of numbers that we were really working with. Well, in this case, instead of taking the square root, we're just going to take this and divide it by the expected value. It's almost like taking the square root, right? Because these two numbers are probably not very different, right? So I'm going to do that for each one of these cells. So when I do it to each one of these cells, I'm going to add up the value that I get for one. So all I'm doing is taking the sum of all of these values. And that's what my chi-square value is equal to, right? So in this instance, it's going to be 25 divided by, well, the first cell, the expected value is 10, right? It's going to be 2.5. The second cell, right, 35 minus 40 is 25 over 40, 25 over 40, right? What does that come out to be? We would want to volunteer a number here. 25 over 40 should be a 5/8, which is 0.625, right? And 5 squared, the 25 minus 30 is squared at, it's 25 divided by 30, my expected value, and that's going to be equal to, help me out here, somebody. What's that? How much? Anybody got a calculator? I'll do it myself.
25 divided by 30?
Yeah.
0.83.
0.83? Okay, 0.83. And finally, 125 minus 125, the squared, the difference, 25 divided by 125 over 120. What does that come out to? I'm going to say 0.04, let's say.
That's 25 divided by 120, right?
25 divided by 120 is about 0.2. Good, close enough. Okay, so I'm going to add all these together, right? So 0.62, this is going to be 3.1 roughly, and 3.1, about 4, about 4.2.
4.155.
Oh, good work. 4.155. So that's what my number for chi-square adds up to, right? That's what my chi-square value. This is chi-square is equal to this, right? So now if I go over here and I take a look at what a chi-square distribution looks like, I'm going to take the chi-square distribution for 1 degree of freedom. Okay, all of these curves, just like the t-distribution, each one looks just a little bit different in shape. Okay, but basically what it tells us is that as the value of chi-square goes up, right? I have a curve that the area of that curve represents the probability that I'll get a value for chi-squared that high. It starts off pretty low, maybe not zero, but pretty low, because it's unlikely that I'll get a chi-square of zero. Where would I get a chi-square of zero? When there's no difference between when the expected value is exactly the same. I wouldn't expect that to happen very likely. So in the beginning, I would expect to get a little bit of a difference going up. But then after I reach a certain point, I would expect that to diminish. The probability of getting that big a value to start diminishing. And then it keeps going over and keeps going over until kind of almost asymptotically just go all the way over to the end. So the probability of, let's say that this is, for 1 degree of freedom, this is 1, 2, 3, 4, 5, etc. The probability of getting 2, anything, a chi-square under 2, is the area under this distribution. Might be like 50%, right? So if there's only 50% chance that I would get that value, if there's 50% chance I get that value, if there's no association, just by chance, I don't want to reject my null hypothesis and say there is an association. But if I keep going over, as chi-squares gets bigger and bigger, it gets less likely that I would get that outcome if there is if there's no association. So if I go all the way over here to number 3.84, I'm going to show you on a table where I got that number from. If I go over here to a chi-square that's equal to 3.84, what do you think the area to the right of that is? That's only 5%. So in other words, I would get that big a chi-square value when there's no association between the exposure and the outcome for my categorical variables. I would only get that big a chi-square value less than 5% of the time. So then I can say, well, I'm rejecting that null hypothesis that there's no association, because I can say that and only have a 5% or less risk of doing that. In other words, that satisfies my alpha of 0.05. Oh, I'm sorry, 5% chance of being wrong if I reject the null hypothesis. In other words, this represents the probability that you would get this big a chi-square when there's really no difference between the observed values and the expected values, right? So you want a number that's bigger than 3.84, right, in order to make this area smaller than 5%, so that you can say this outcome wouldn't be very likely if there's no association. It would only occur less than this amount of time. If your alpha was 0.01, you would have to choose a chi-square that would leave only 1% of this curve at the end. Okay, so let's take a look if I can't find a chi-square table. Okay, and sure enough, there it is. So just so you can see where I got that, for a probability of 5%, an alpha of 5%, if I have 1 degree of freedom, my chi-square value is going to be 3.841. Okay, in other words, that's my critical value. If I get a chi-square value of bigger than 3.841, then the chances I'll be wrong if I reject the null hypothesis is less than 5%. If my alpha was 1%, I would have to have a chi-square value of 6.6 in order to reject the null hypothesis. Okay. Remember somebody mentioned a handedness, you mentioned that, oh, maybe there's more than 2 values. Someone might say, well, gee, what about if a person's ambidextrous? What if he replies he's ambidextrous? Well, what does that do to our table? Let me go back to our table. Okay, what does that do to our table? What that does to our table now is that we still have 2 genders. Whoops. Right, we still have 2 values for gender, male and female. But now we can have left-handed, we can have right-handed, or we can have ambidextrous. So we have 3 values for the categorical variable handedness instead of 2 values. But we can still do the same thing, except this time instead of 4 cells that we calculate a value for, observed minus expected over squared over expected, now we have 6 cells that we're calculating it for when we compare the observed and the expected values. Okay, so how many degrees of freedom does this represent? How do we calculate degrees of freedom again? Is equal to the number of rows minus 1 times the number of columns minus 1, right? So what does that come out to? 2, right? 2 rows minus 1 is 1. 3 columns minus 1 is 2. 1 times 2 is 2, so it's 2 degrees of freedom. So now my critical value for my 5%, my alpha is equal 5%. My critical value now on that table for chi-square is no longer 3.84. Now it's 5.99, which makes sense. Now I'm going to have a bigger number for chi-square because I'm calculating it for more boxes. Okay? So could this be a simpler calculation? Right? It's pretty simple, right? Now, let's talk about one of the issues here. When we calculated our observed values for this table, I used really nice round numbers. In real life, we're likely to come up with a situation where okay, click on that. In real life, 2 by 2 tables, observed and expected. Right? Okay, we might come up with, I'm going to say 36, 94, 11, 42. My expected values, 27.3, 14.1, 82.3, 46.7. What's happening here with my expected values? They're calculated based on the prevalence or the incidence and multiplied by the numbers that we started with in observed values, right? So they're likely to be fractional numbers, right? In fact, if remember the population I talked about before, we said 30 out of 100, right? Well, in fact, that population might really have a value of 29.5 out of 100, right? Because we could represent thousands of people. But I can only have a whole number in there because in my observed values, I'm counting actual people. So in my observed values, I can never have a fractional number, even though the real value it represents in a population could be a half a unit below that or a half a unit above that, for instance, right, to be representative. So one of the things that we can do when we have a 2 by 2 table is that we can do something that kind of makes up for that extra level of uncertainty by making it a more conservative test. And what we can do there is we can say, instead of saying chi-square is equal to observed minus expected squared over expected, how about if I just subtract, I take the difference observed minus expected and subtract 0.5 from each one of those numbers and then square it. Okay, that's called a continuity correction, right? Or is that the Yates? I guess you call that the Yates correction also, right? So we're kind of making up for that lack of continuity in these values that we're collecting, right? And what is that going to do to your chi-square value? It's going to make it automatically smaller, so it's a more conservative estimate of whether you can reject the null hypothesis or not. Okay, so
Should we do that like that standard chi-square equation?
I think for small sample sizes, am I right, Levi? You use it exclusively usually for 2 by 2 tables and for small sample sizes. Yeah.
Just for 2 by 2 tables.
Just for but not for large samples though, right?
For any sample.
Any sample?
2 by 2. I mean, it makes less of a difference for large samples.
Yeah. Okay, so you could do it for anytime you do a 2 by 2 table, use the continuity correction. You're going to notice when we use SPSS, it's going to calculate both the chi-square observed minus expected over expected, squared over expected, and it's going to also calculate the version with the continuity, with this 0.5 continuity correction. Okay, so it's going to give you the option of which one you want to use. Okay, so Matter of fact, before we go back and take a look at this from another angle, let's actually do it using SPSS. Okay, and let me see if I have a data set I can use here. Nope, that's not what I want. I think I have another one back here. Okay, let me open up this SPSS file. Now, chi-square you can calculate easy enough using Excel, right, without too much of a problem. But if you have a very large data set, okay, now in this data, we have, go into our variables, take a look what our variables are. We have 3 categorical variables. One of them is smoking status, whether a person's a smoker or not a smoker. And if we go in here, 1 represents a smoker, 2 represents non-smoker. Variable 2 is presence of aortic stenosis. That's narrowing of the coronary arteries, right? 1 would be yes, they have that condition. 2 would be no. And the third variable we have here is gender, and that's also labeled. That's labeled 0 and 1 for female and male. So I go back to my data view. And if I want to organize this data, say, so subject number 1 is not a non-smoker, does not have aortic stenosis, and is female. Patient number 2 is so on and so forth. We could take a look at all of them individually. There are, how many subjects? So we can get stopped there. There's 215 subjects. I'm going to first organize this into a table. The way I'm going to do that is I'm going to go to Analyze, and I'm going to go to Descriptive Statistics, and I'm going to go down to crosstabs, because what I want to do is build one of these tables, a crosstab table or a contingency table. So I'm going to crosstabs, and like I said, I usually like to put the exposure in the rows. The exposure, in this case, let's call it smoking status. And the outcome or the disease in the columns, let's call that the presence of aortic stenosis. So now I'm going to go up here to cells. And right now, the only thing it's going to give me in the output is the observed values. Okay, I'm going to click OK. For right now, that's enough for me. In statistics, nothing's checked off. Okay, I'll come back to that later. So I'll just go ahead and run this analysis. Okay, and here's the analysis. Here's what it came up with. I want to bring this up higher so we can see it a little bit better. I'll do it again. Analyze descriptive statistics, crosstabs. I move in smoking into the rows and smoking status into rows and presence of stenosis into the columns. Click OK. And here we go. You can see it at the top here now. So what do I have? I have, out of these 215 patients, I have 54 that are smokers and have aortic stenosis. I have 40 that don't have, that are smokers and don't have stenosis, and we have 44 non-smokers that have stenosis and 77 non-smokers that do not have stenosis, right? So this might be maybe a population of people that are going for follow-up testing after some preliminary screening or something like that, and it's suspected they might have it. Okay, so because obviously the prevalence is really high in this group. Okay, so this is our expected, this is our observed values. So now if we want to calculate our expected values for this group, what would it be? Well, we take 98 over 215, right? Find out what that fraction is, multiply it by 94 to get the yeses, and multiply it by 121 to get this value. And then again, once we got one value, all the others fall into place, right? So now let's take a look at what the expected values might look like. So I'm going to go up to Analyze, Descriptive Statistics, Crosstabs. I'm going to go back into Cells, and this time I'll ask it to calculate the expected values for me. And click OK. Okay, let's see what we got. Again, I'm going to do it twice, so that actually, tell you the truth, maybe a better way for me to be just to narrow this up so I can scroll it up. Okay, so in this case, I've got both of these. Instead of making two tables, it just summarizes the data into the same table. So I've got 54 people. That the observed value here was 54. The expected value is a bit lower. It was expected to be 42.8. My observed value is 44. My expected cases would have been 55.2 is what I would have expected if there were no association between smoking and stenosis. Okay, so now,
How does it know that? Who is that based on the raw numbers? Like, if you were just, it's great. You know, like the prevalence issue? Like, how does it know what, how does it know?
it judged the prevalence from our observed values. It calculated it from our observed values. In other words, our observed values said on the average, whether, forgetting about the exposure, 98 out of 215 people in this population had stenosis. So that's where it got. That's basically where it got it. Just like we did before with the tables we were working on manually. Okay, so now let's actually go ahead and calculate chi-square. So I'm going to analyze descriptive statistics. Descriptives. Whoops, didn't mean to hit that. Descriptive statistics. Cross tabs. Analyze descriptive statistics. Cross tabs. There we go. This time I'm going to go up into statistics. I'm going to ask it to calculate the chi-square value for me. And I'm going to click OK. Okay, let's see what it did this time. Well, indeed, it gave me back my tables again because I still had that the expected values and the observed values turned on for my output, and actually calculated chi-square, 9.48. Right, degrees of freedom is 1. What can you tell me about 9? If you saw a 2x2 table, and I got a chi-square value of 9.4, what did we say the critical value was for 5%? Alpha's 5%. 3.84. So if we exceeded the critical value, you would expect that to be less than 5% chance of being wrong if we reject the null hypothesis. Well, SPSS has a little bit of an advantage here. It actually calculates the probability of being wrong if you reject the null hypothesis. So not only do we know it's going to be less than 5% because we exceeded the critical value, but we know, in fact, it's going to be less than 1%. So we could even, it's 0.002, so we could reject the null hypothesis even at alpha is equal to 0.1. Okay, so now that's if I use Pearson's chi-square to calculate it. What did we say about Pearson's chi-square? It doesn't use the continuity correction, right? It's just literally the calculation that we did before. So if we want to be more conservative and use the continuity correction, in other words, observed values, observed minus expected, minus 0.5 squared, over the expected values for each one of the cells. Well, now our value for chi-square is 8.649. Still comparing it to the critical value of chi-square, 3.84. We still reject the null hypothesis at 5%. Well, how about a 1%? Well, we got kind of lucked out there. We still rejected a 1%. This is a little bit more likely that we would get this outcome if there were no association than if we use Pearson's chi-square. But both of them were pretty far away from what we needed. Okay, so this is literally the same calculation you would do by hand, except we did it in an instant here, right? Organized it, put it into tables, calculated it. We didn't have to go to a table for the critical value of chi-square.
Show you the critical value?
It doesn't show you the critical value, no. Okay, that you can go to a table, but it's just even better. It shows you what the significance or the probability of getting that extreme an outcome if there's no association. In other words, that's how far out on that chi-square distribution you are. You're at the point where there's only 0.2% chance of getting that if there's no difference between smokers and non-smokers. Okay, so now let's take a look at this from another perspective. Okay, and that is, I'm going to go back to our tables. See if I can't do this without messing this up. Okay, 15, 35, 25, 125. 15, 50, 15, 25. Okay, do my personal Alzheimer's test, try and remember what that table had in it. Don't laugh. Okay. Okay, 15, 25, 50, 150. Okay, so notice that's all I had to remember. 35, 125. Okay, so this is 40, and this is 200, this is 160. Okay, looks like I got away. I'm good for another semester. HIV, that's negative. Okay, and I think this was male and female. Oh no, this was drug users, IV drug users, and non-IV drug users. Okay, so let's look at this from another perspective. Given what we see here on these observed values, these values that we actually took, let me just check on how guys are doing online there. Lose them. Okay, guys, it seems like we're okay. Even got a couple of bits of help there. Okay. All right, so looking at this data, these observed values, what does it look like the probability that if you're an IV drug user in this population, what's the probability that you are HIV positive? In other words, what's your risk for being HIV positive? Yeah, I like that, right? I'm going to call this risk, right? Your risk of being HIV positive is 15 over 50 or 30%, right? What is your risk if you're not an IV drug user in this population? They may have other risks as well. Maybe, sexual practices, whatever, may have other risk factors as well, because obviously this population is at high risk, whether an IV drug user or not. So what is the risk there? It's 25 over 150, right? That is 1 over 6, right? Which 0.16. I'm going to leave it at 0.16. Okay, so your risk of being HIV positive is 30% if you're an IV drug user, and only 16% if you're not an IV drug user in this population. Well, let me take a look. How does this look relative one to the other? One of the ways I can compare these is I'm going to call this relative risk, or another word for it is risk ratio. So anytime you hear me use the term ratio, it means I'm going to divide one number by another. 0.30 divided by 0.16. That's my risk ratio, or relative risk, if you want to call it that, right? And what does that come out to? That's going to come out to roughly about 1.8 or something like 805? 875. Okay, I'm sorry, no, I'm sorry, it's 1.75, is that right?
1.875.
875. Okay, I'm going to change that. I'm going to round it off to 1.9. What does this tell us? This tells us that if you're an IV drug user in this population, you're 1.9 times, you're almost twice as likely to be HIV positive than if you're not an IV drug user, right? Well, that's pretty interesting because now this gives us a little bit more of a handle on what the risk is. In other words, isn't it more intuitive to tell someone, well, your chi-square value is this, and we know that there's this level of certainty that there's an association that if you use IV drug use, you're an IV drug user, you're more likely to be HIV positive. Isn't it more intuitive to tell someone, you're twice as likely to be HIV positive if you use IV drugs, right? It's an easy way, a good way to get a handle on what the increased risk is. And you've seen this in the papers all the time, right? In other words, if you eat 2 packs of gum a day, you're 1.9 times as likely to have your teeth fall out or something like that. You see that idea, that odds ratio or that risk ratio communicated in many different ways. Cholesterol, weight, how the weight has your weight, your cholesterol, your exercise level, your whatever, how all of these different factors figure into, say, increased cardiac risk or something like that. Well, that's one way to describe the relative risk between these two, between no exposure and exposure. Another way to describe it is to describe it instead of in terms of risk, in terms of odds. Let's talk about odds. Odds is something that's a little less intuitive than risk is. If you go to the track and the odds on a horse winning are 3 to 1. What that means is that if they ran the race 4 times, they'd expect the horse to lose 3 times and win once. Why is that important? Because if you bet $1, right, you get $3 back if the horse wins, right? So it is an easy way to do calculations for the payoff for a race. So you don't have to be a genius to sit at the rail and watch the horses run by, right? So it's convenient for the track. Not everybody at the track has taken advanced algebra or solid geometry or anything like that. So it's a convenient way to understand what the payoff is, right? So we use it here also. It's a little less intuitive than risk is, but we calculate it the same way. How many people do we have that were IV drug users? 50, right? Okay. Well, we have 15 that were IV drug users that are HIV positive, and 35 that are not HIV positive. So our odds of being HIV positive are 15 over 35, right? So what's that number come out to? 15 over 35?
.42.
You beat me to it. 0.42? 0.42. That's our odds, right? So you could extend that. If you had 100 people, 42 would be HIV positive, 58 would not be HIV positive, right? Or if you had 1,000 people, you would expect 420 would be HIV positive, 580 would not be HIV positive.
That's the odds for IV drug users.
For IV drug users, exactly right. Let's do it now for non-IV drug users. What's it going to be here? You guys tell me. Exactly right. Right. So in fact, if you look at like the notes that I've put up and stuff like that, you'll see in a lot of cases, you'll see me put in a table A, B, C, D. This is A plus B. This is C plus D. And for risk, I would say A over A plus B, right? Over, for relative risk, C over C plus D, right? That's my relative risk. For odds ratio, it's going to be A over B divided by C over D, right? So that's how you would calculate it if you forget about this. But it's just as intuitive to do it this way. So this is going to be 0.5, right? 0.2, correct? Okay, so now, just like before, we're going to calculate an odds ratio, which is just going to be 0.42 over 0.2, right? So it's going to be 2.05 or something like that, 2.05. Okay, so how's our odds ratio and risk ratio? How would they relate? They're pretty close to one another, aren't they? Yes.
Aren't you interested also if you do like 15 over 40 and look at the odds of?
Well, that's now you're looking at HIV. Actually, if you just turned the chart around, didn't you?
Yeah.
You're looking at HIV being the exposure and IV drug use being the outcome, right?
Yeah.
It really doesn't make too much sense that way, right? I mean, there's times when you might actually want to flip these things around to take a look at them. But from my perspective, I think probably if we look at it in terms of what would cause the other to change, I would say that the independent variable is the IV drug use, and the dependent one is the outcome of HIV positive or not. In other words, being HIV positive would not likely cause you to be, from a physical perspective,
Yeah.
HIV would not cause you to be an IV drug user. But an IV drug user, whether you use IV drugs or not, might cause you to be more likely to be HIV positive. But there are instances where you might turn these around, right? I don't think in this one right now. Okay, but that's a good thought. Okay, but they're a little bit different, right? Personally, I find relative risk to be more intuitive, right? Because it's easier to understand. But odds ratio makes its way into a lot more abstracts and papers and so on and so forth. Okay, I won't go into the reasons why it might be a little bit more popular. Okay, but what's important now is this gives you a measure of how big the effect is. If the odds ratio is 1.1, well, that's a lot different than having an odds ratio of 3.1. right? Where you might say, oh, wow, that's an important public health effect. If the bigger that number is, the more important the health effect is, right? Okay, or the outcome of public health effect might be. So that's an important number for us. Now, let me ask you something. If there's no association between HIV drug use and IV drug use and HIV status, what would you expect the relative risk and the odds ratio to be?
One.
Bingo, right? You guys see why they would be one? Because then you would expect the rate at which people are getting HIV if they're drug users to be the same as the rate as we would expect if they were not IV drug users. In other words, what we would put into our expected values, right? Our expected, if you did the expected values of table of expected values, if you did the same calculation, the relative risk and the odds ratios would both come out to be one, because it's just based on the prevalence anyway, right? Saying we just be doing the same calculation backwards. Okay, so we have to look at this odds ratio and we have to say to ourselves, well, it came out 1.9. How likely is it that I would get a value of 1.9 by chance? What if that value were only 1.1 or 1.5 or 3.9? Where do I draw the line? In other words, I wouldn't expect, remember, just like I wouldn't expect my expected values to be exactly the same as my observed values, I wouldn't expect my odds ratio or my relative risk to be exactly one. So now the question is, how big does it have to be in order for me to reject the null hypothesis that the relative risk or the odds ratio is equal to one, right? How would I determine that? What do I need to know about that odds ratio? Remember, it's a point value. When we have a point value like, what's that? We need a confidence interval, exactly right. And what do we need not to be in that confidence interval? The number one, exactly right. So let's go back to SPSS, right? Because I don't think in this class we're necessarily going to ask you to calculate the confidence interval for the odds ratio. I'm going to go to Analyze, Descriptive Statistics, Crosstabs, except this time I'm going to add on another value in statistics called risk. Where is it? It's down here. And I'm going to click Continue. Oh, the other thing I'm going to do is, before I do that, I'm going to go into Cells and ask it to calculate. I'm going to turn off expected values. I'm going to ask it to calculate percentages by rows, just so you can see it. And here is our percentages by rows. 57%, 42%, 36%, 100%. So I would expect this is my percentage of people that were had aortic stenosis that were smokers was 57%. That comes from 54 over 94, and no aortic stenosis for non-smokers of 44 out of 121 came out to be 36. So my relative risk is 57% divided by 36%. Right? My odds ratio is going to be 54 over 40 divided by 44 over 77. If I scroll down here, I only see Pearson's chi-square. I have to go back to Analyze, Descriptive Statistics, Crosstabs. So this time I'm going to turn on that calculation for risk. Wrong one. Statistics, risk, continue. Okay. Okay, so let's take a look at this. I got the same calculation for chi-square as before, except we got a new box down here. Odds ratio for smoking status, yes or no? Our odds ratio is 2.36. And our confidence interval for that odds ratio is 1.361 to 4.1. So that does not include the number one. So what is our null hypothesis? First of all, what's our null hypothesis when we're doing chi-square? Well, no, when we're doing chi-square. No, chi-square is not one, right? It's going to be, chi-square is always going to be some number, right? Well, it's going to be hard to define a specific number for chi-square because it could be anything under 3.84 we would fail to reject. Well, how about if we just say that there's no association between the exposure and the outcome? There's no association between smoking and stenosis for chi-square. Our alternative hypothesis is there is an association between smoking and stenosis. For our odds ratio or relative risk, that's a little bit simpler, right? We can say relative risk is equal to 1 for our null hypothesis, or relative risk is not equal to 1, right? Same deal as I had for chi-square, except now I can express it as a number. And in order for me to say the relative risk at alpha is equal to 0.05, I would have to make sure that my 95% confidence interval doesn't contain 1. So in this case, can I reject my null hypothesis? Yeah, it doesn't contain 1, so we can reject our null hypothesis. How about this next one? For cohort, presence of aortic stenosis equals yes, 1.58. You want to know something? I'm going to go back up here. And I'll bet you if you took 57.4 and divided it by 36.4, you would get the number 1.58. So what is that number? That number is your relative risk. Same deal there. Relative risk, of course, doesn't contain 1, so you can also reject the null hypothesis for the relative risk is equal to 1. Okay, so you can get SPSS to do all of these calculations for you.
But if it's 57.4 divided by 36.4.
That came from, remember, came from A over A plus B, which is 54 over 94,
Okay.
right? That's 57. These are the percentages by rows.
Right.
So 54 over 94 is 57%, and 44 over 121 is 36%. So I'm just taking the risk for smoking and dividing by the risk for non-smoking, and that gives me my relative risk, right? In other words, that's 54 over 94 divided by 44 over 121. A over A plus B divided by C over C plus D. Right? Right? It's the same way we calculated if we had done manually. And my odds ratio, that what was it again?
2.36.
Yeah, that came from, where'd that come from? 54 divided by 40 is my odds for smokers, and 54 divided by 27 is my odds for non-smokers. So 54 divided by 40 divided by 44 divided by 77 is my odds ratio. And that's where that 2.8, whatever it was, came from.
There's a little more of a gap there between the risk ratio and the odds ratio.
Yeah, there is, right. Yeah, they're not always the same, right? So a lot has to do with sample size and the differences between the differences in the risks themselves and so on. So yeah, they're not going to come out exactly the same, but you'll always get the same result for whether or not you can reject the null hypothesis. Okay, I'll see if I can't find a link somewhere to an argument on why you might use one versus the other. Personally, I think relative risk is so much more intuitive that I'm not sure why so many studies are in love with, publishing odds ratios.
You get kind of used to it because it's
Yeah, everybody's doing it, so you do it too. Right, exactly.
yeah. And your software spits out odds ratios.
Yeah. Yeah, in fact, it's easier if you read this box. It's actually easier to interpret which of these answers is the odd ratio than to interpret which of these is the relative risk. If you look at this last one is just remember we were talking about flipping the table? This last number at the bottom is just the inverse of the relative risk, right? If you had the exposures turned upside down. In other words, you put no IV drug use on top and IV drug use on the bottom. Personally, like I said, in order to make this a little bit easier to understand when you print out these tables, I like to put the exposure in the rows and the outcomes in the columns. Okay. In addition to that, I like to put the bad one on top, like in other words, in this case, smoking, right? So if I expect it to increase the rate of HIV, I like to put that on top. And the way to get it on top is to code it alphabetically so it comes below the other alternative. In other words, put the smokers in as 1 and put the non-smokers in as value 2, right? That'll make sure the smokers are on top. What'll that do for you? That'll give you an odds ratio or relative risk that's bigger than 1, right? Which is easy to handle. If I put the non-smokers on top and the smokers on the bottom, what would my odds ratio come out to be? It would have come out to be something like 0.4. And what would that have told you about the relationship between smoking and stenosis. It would tell you that it's less than 1, which would mean that not smoking is protective, right? So if you have a relative risk or an odds ratio that's less than 1, it means that the exposure is protective. If you have an odds ratio that's bigger than 1, it means that the exposure causes the disease or is not protective. Right. So, and in fact, you can get both results just by flipping smoking and non-smoking in the rows. Similar with the disease. It is a little bit more intuitive if you put the column with the disease in the left and no disease on the right. So, for instance, cancer, 1, no cancer, 2. So, and that'll like kind of make things work a little bit better. And you can transform all this data. So if it comes with already pre-coded differently. So now why is this important to us? Just to close off, I want to open up the community health survey, the data from the community health survey. Actually, I'll open the code book. Here's the code book. So each one of these pages has a variable and a definition of what that variable is. Okay, diabetes, yes and no, categorical variable. Ever been told you have asthma? Yes, no. Current asthma status. Mood, yes, no, well, yeses and nos. Nutrition, 1 to 4 servings, 5 servings. It doesn't actually give you a number of servings, does it? It gives you categories of the servings, so on and so forth. Let's see. Raw data. How often do you drink sugary drinks? 0 to 20. Okay. Also categorical variables. Soda size. They even code that as a categorical variable rather than give you an actual raw number. Now, there are numerical variables in here, but by and large, 80–90% of these variables are categorical variables, right? So you'll need something that you can evaluate these relationships with that will work with categorical variables. There's your chi-square, there's your odds ratio, there's your relative risk, right? Now, there are numerical variables in there. Let me see if I can't find the actual file itself. CHS 2014 SAV. Here we go. Wait for a second while it opens up. And let's see. I got a comment here. You can't use relative risk if you can't establish temporal order. Can't use relative risk. Temporal order means order in time. Oh yeah, okay. You're saying that, in other words, if I don't know if the IV drug use came after or before the HIV diagnosis, I can't. That's kind of a problem. Yes, but thanks for complicating things. We don't appreciate it. But you're absolutely right, unfortunately. Yeah. But yeah, sure, of course. There's all sorts of landmines in this data that if you really take a close look at it, that you really have to be concerned about. All sorts of confounding factors, all sorts of an issue like that, whether or not, in fact, maybe they didn't, maybe that was part of the survey. They asked them, did you use IV drug use before you were diagnosed? Or before you were tested, let's say. That's good work. Thank you. Okay, let me see if that opened up. Here we go. Okay. So if I'm going to go back to the variable view here, let me move this out of the way. And you'll notice that, look, see, we do have some scalar variables in here. Now, keep in mind, SPSS is interpreting this, so it's guessing at whether they're nominal or scalar. But let's say survey. Oh, these are survey weights. That's not what I want. Okay, let me see if I can't sort this. Edit. Let's see. Where's my sort variable again? Transform. Encode. Data should be in here, I think. There it is. Sort cases. Okay. Oh, no, that's not what I want. Data sort variables. And I want to sort them by the measure. Okay. Okay, let me get the window back. Okay, so those are all nominal here. Let me go down. The scalar one's down here. Okay, so what do we have here? We have soda, ounces of soda, number of sweetened drinks. We have total times, total number of minutes per day sitting. We have there are some numerical variables for you to play with, but for the most part, most of that data, even the numerical data, has been summarized in categories in this data set. And so the key here is now we have a tool to evaluate associations involving categorical variables. So we got a tool for numerical variables where there's two means, two groups, numerical variables where there's more than two groups. We have a tool for calculating, for looking for an association between categorical variables, for determining the strength of association, like odds or relative risk for categorical variables. We are missing a way to look at ways that we can evaluate whether one numerical variable is associated with another numerical variable. In other words, I'll give you an important one. That's one that's important to all of us. I have known since high school that the price of a subway ride is the same as a slice of pizza, right? So how would you prove that? You would go back over time and you would, for each year, figure out what was the price of a slice of pizza and what was the price of getting on the subway, and you would plot a point for each one of those and see if they were associated. Is as the subway fare increased, did the pizza size of the cost of pizza increase as well? That's correlation. And we're going to talk about that next week, correlation and regression. So we have numerical variables that we're going to compare point estimates of like means or proportions, categorical variables, and now we're going to have next week we're going to way to see if two numerical variables are associated with one another.